Okay, now the majority of theorists have assumed that short-term memory and long-term memory are distinct systems, both conceptually and in terms of the sort of neural basis. On the next few slides, we're going to consider some of the different models that are proposed to explain the way that short and long-term memory systems are related to each other. So first we're going to consider one of the sort of most famous approaches to memory, the multi-store model of memory, where we make this very clear distinction between long and short-term memory. And then we're going to focus on the working model of memory, so proposed by Baddeley and Hitch. It's a sort of alternative view that combines short-term memory functioning and processing. So Atkinson and Schifrin's multi-store model basically proposed that we have several stages through which information flows before it can be stored in long-term memory. And this was a very influential model and has an entire architecture of cognitive processing here. So if we follow through from the left-hand side, we're first beginning off with receiving what they class as environmental input. You can just think of this as all sensory input, so light, sounds, touch, etc. This sensory or environmental input is then passed to the sensory registers, and these are the areas that are going to hold this information for a fraction of a second. So again, at this stage, anything that we don't pay attention to is going to get neglected and degraded from this sensory register very quickly. And again, we've got distinct stores for visual, auditory, haptic, etc. So haptic is touch-based. Now, whatever it is that we end up paying attention to, then this gets passed to a short-term memory store. And this short-term memory store can hold and also do some processing on the information here. So it's here where we can store this 7 plus or minus 2 things for less than 30 seconds or whatever we agree the capacity and the duration of short-term memory is. And then the argument went that if you have sufficient rehearsal of the information, so if that short-term memory is reactivated repeatedly and enough times, it'll get transferred to a long-term memory store. Okay, let's jump into it and have a look at some of those different stages proposed in the model. And the first of these is the idea that we've got these sensory registers. And this is sort of undisputed. There's lots of evidence supporting the existence of these sensory registers. And we're going to consider just 2 here. One's for visual and auditory information. So we've got this iconic memory store, which is going to store a very rich, detailed representation of all visual input for just this very brief period of time. And again, it's only what we're attending to that ends up getting processed and actually accesses into our short-term memory store. But one way you can think of this is if you imagine at night time that you've got a very bright light or something like a sparkler that you're moving around. If you move it around in a circular motion, it can very often you perceive that as looking like it's a continuous circle, whereas there's no sort of physical trace as the sparkler moves around, but it's just the fact within our iconic memory we're sort of seeing the remnants of this trace that moves around. Similarly, with echoic memory, we also have a store for auditory information, so we can store all of that auditory input that comes in for a very brief period of time that looks like sort of around about sub 2 seconds. And one creative experiment that was designed to measure echoic memory was by Gutmann and Jaws. And to do this, they used computer-generated segments of white noise. So this is basically sounds that are composed of randomly mixed together different frequencies. So when you're listening to this, it just sounds like a sh sound. You can't describe it, you can't memorize what it is. However, what they did in their study was then take sections of this white noise and put together a repeating pattern of white noise without any gaps between the repetitions. If the repeating segment of white noise lasted longer than a few seconds, all that subjects would report hearing is just, all I can hear is a shh sound. But if the repeated segment was less than 2 seconds, subjects then suddenly realised that they were hearing some sound that seemed to be repeating. They still couldn't describe it. It didn't really sound like anything. It sounds like a shush sound. But they knew something was being repeated. So in order to detect this repeating pattern of random frequencies, subjects must be using some memory system that's capable of preserving an exact copy of the noise from one repetition to the next. And that's exactly what echoic memory is doing. So it's just preserving an exact pattern of the sound that has been input for 1 or 2 seconds. Another example that's less scientific but relates to real life that sort of demonstrates the echoic memory is if somebody says, "What time is it?" and you go, "What did you say?" "Oh, it's 2:30. The second person is hearing this question after they've asked, "What did you say?" So the idea being that this echoic memory is basically holding the sound of the question for a second or two. So even if you're kind of not paying attention to the words when they've been said, you can hear them when you then turn your attention to focus on what was that thing that I think I've just heard somebody else say. So this can be annoying to the person who starts repeating the question, only to be interrupted by the answer. So what evidence exists that we have an iconic store? Also, how much visual information can we retain in this iconic store? So some of the key characteristics of iconic memory were demonstrated in a classic experiment by George Sperling, it's back in the 1960s. And in this study, Sperling presented his subjects with a visual display that has a 3x4 array of letters, so as you can see in the top right here. And they presented this array very briefly. So it's for 50 milliseconds. It is enough that you can make one glance. So you can't make saccades around the visual scene here. Typically you'd focus on a fixation cross in the middle and you just get this one look at it. What you then do is ask participants to indicate what was the contents of the array. So how many of those letters can you correctly recall? Now in the whole report procedure, subjects were instructed to report all of the letters that they could remember in this array. And what you find is when participants do this, on average they're capable of recalling 4.5 of the 12 letters. So I mean, that's not bad. That's a reasonable degree of accuracy. But is that really accurate? And Sperling was interested in whether maybe people actually saw more, so more information was stored in this iconic memory, but while they're reporting this information, so while you're saying it aloud, yeah, I've seen HBST, during this period you end up forgetting the other stimuli that you focused on. So to test this idea, Sperling designed what he called a partial report procedure. And in this version now you've got the letters presented in these 3 different rows, and after they've been presented you would then listen to a tone. So it'd be a high, medium or low pitched tone that would indicate which row do you need to recall. The reason that they used a tone is so that it wouldn't distract or interfere with anything that's in the iconic store. So by doing this, maybe we can get a better insight into the capacity of this memory store. But then in this design, they continued to be a little bit greedy of what we could understand, and they wanted to get a measure of what is the duration of the iconic memory store as well. So to do this, they would then vary, after that array has disappeared, they would present the tone with a different level of delay. So in some trials, it would actually appear 10 milliseconds before the array disappears, so almost immediately you know which line you've got to recall, which row you've got to recall, and then other trials it would be delayed by up to a second. And if we're thinking that this iconic store doesn't hold things for very long, your performance is probably going to be quite poor if you don't know which row to recall from after a second of doing this. So let's have a look at the data. Let's see what happens. The first thing we can see is the data's plotted there for the whole report method, So on the right hand side, the little kind of bar that moves up with the dot, memory there is on average 4.5 out of the 12. But if we now look at the line with the dots towards the left hand side, we can see the response or estimated number of letters that are recalled during the partial report method. And using this, you can see that iconic memory is much better. And actually, people are storing almost everything that they've observed in the array. So when there is no delay, participants could recall on average 3 out of the 4 letters within that row, which they then make an inference that if so you don't know in advance which of these rows you're going to have to recall. You're only getting one look at it. If you're capable of recalling 3 out of the 4 on that one row, that's going to mean you have been attending to 9 out of the 12 letters in the entire array that's there. And then as the delay increased, the number of items that are getting recalled pretty strongly degraded. So certainly up to sort of 150 to 300 milliseconds afterwards. So this is evidence again for the sort of very short storage of items in this iconic memory store. In the following video, let's look at an example of the task that Sperling would have used. It's tough, eh? I'm sure many of you saw the P, but what about the rest of it? How many did you get correct out of those? So again, you should be focusing on the fixation cross at the start of each of these trials. Okay, the next stage of the model is the short-term memory store. So if we just go back to think about in the sensory register, the stuff that's entering there, we don't have any real conscious insight or access to. And it's only the things that we end up attending to or end up processing to some degree that actually transfers into this short-term memory store. And then for Atkinson and Schifrin, they argued that it holds and processes information across all different modalities. So whether that information is coming from the visual or the echoic or the iconic sensory registers, both of those would come into one central sort of modality independent short-term memory store. From within the short-term memory store, if we want to retain stuff there or transfer things to long-term memory, what's required is reactivation and rehearsal of that information that's there. Otherwise it's going to decay or we'll forget it within 30 seconds or whenever your sort of cut-off of the duration of short-term memory is. And then the final stage of the multi-store model is this long-term memory, so permanent memory store. And this is where all information that's going to be stored after it's been rehearsed. And they argue that the probability of any piece of information being encoded into long-term memory is directly related to the amount of time that it spends in short-term memory. So in other words, the more that you end up rehearsing and repeating this information in short-term memory, the more likely it is to transfer to long-term memory. But that's a topic for another lecture. So Atkinson and Schifrin's model was really influential, so particularly from a kind of cognitive psychology perspective, using these flow diagrams to illustrate the different processes was a kind of real revolutionary step forward. But it had some fundamental flaws to it, and it makes some incorrect assumptions as well that do limit its ability to account for sort of all human memory processing. So the first one of these is the idea that short-term memory is modality independent. And we know now there's pretty convincing evidence that this isn't the case. We have definitely different subsystems that seem to be responsible for storing visuospatial and auditory information. And how do we know this? Well, we know that when you're doing tasks that involve visuospatial versus doing tasks that involve auditory information, these don't tend to interfere with each other very well. So there's pretty robust evidence that there must be two separate stores that we can access and manipulate at the same time that relate to auditory and visuospatial information. The second one is the idea that there's a single long-term memory store. We know now, it's pretty clear, that there are distinct separate systems for long-term memory. So one's for procedural memories, others for declarative, semantic memories. Number 3, information is in short-term memory before long-term memory. So if we look at that kind of sequential stages in Atkinson and Schifrin's model, what they argue for is that anything in short-term memory cannot have been in long-term memory before. But a lot of the processing in short-term memory often occurs after we've accessed long-term memory. So if you think of the examples I gave you at the start of the lecture, where we explored the idea of chunking. So I gave you like 3-letter trigrams of FBI, CIA, KGB, and combining those together formed a meaningful piece of information. So in order to benefit from that in short-term memory, you had to have accessed your understanding that FBI refers to the Federal Bureau of Investigation in the US, and that means that it is stored as a single chunk. So it doesn't really account for this bidirectional flow of information that occurs. Number 4, rehearsal is required to store information. So yes, that might be a kind of common mechanism, but there are many memories that are not necessarily a product of rehearsal. So there's many times where something could have happened to you and you've not necessarily replayed that event or reactivated that memory trace over, but you can still recall that information.